Mhm. All right, got about 2 more minutes. Feel free to ask me any questions if you have them. All right. Well, it looks like we don't have that many people, but it is time. It's now 5:20. Anybody have any questions before we get started? Oh, another person came in. Oh, we lost one too. All right. So it looks like no questions. I don't see anybody typing any chat stuff. So we're in chapter 10, which we've already started to some extent. I've given you the kinematic equations. We got to make up, of course, uh, the dynamic equations as well, and I got to show you how to use integration to calculate a moment of inertia, that kind of stuff. So let's just begin by working some examples. And the examples are largely like examples that you'd see in the book, but by doing a different example, it gives you yet another example in addition to the book's example. So hopefully that'll help. I'm going to start off by sharing my screen with my iPad. So hopefully this will load up pretty soon. It says a car tire rotates through 8.4 revolutions in 3.00 seconds. A, through how many degrees did it rotate? B, through how many radians? C, what is the average angular speed? And D, how many degrees is in 1 radian? Be sure to use correct symbols for the angular quantities. So that last sentence was basically me reminding myself and, of course, you guys that the first part of trying to learn this new branch of kinematics is to learn the symbols that we use for what. So, for instance, I've already mentioned to you how great a analogy there is between the linear kinematic equations. And specifically what I mean is the analogous terms are in fact x is analogous to theta, x or r vector or x vector, uh, both of which could be called the vector that points to the position of the object at any time t. Well, in place of that, we have theta as a function of t, which isn't a vector quantity, but it gives us a angle from some arbitrary angle that we might call zero, for instance, through which the thing is turned after some period of time t. Of course, t doesn't change from kinematics of linear motion versus kinematics of rotational motion, so the t is going to stay the same. But like I said, x can be replaced, x, y, or z can be replaced with the r vector or the x vector in 3 dimensions. But if you go to any of that in the rotational dynamics, it just goes to theta. So that's the analog there. We found that dx dt was v, the velocity, and similarly d theta dt will be omega, which looks like a cursive W, but it's a Greek letter. That's the angular velocity. And then dv over dt is equal to the acceleration, and its analog would be alpha, and that would be d omega over dt. So alpha is the analog to acceleration, but it specifically means the tangential acceleration. We'll also see that p, the momentum, which we just covered not too long ago, goes to a quantity called L, the angular momentum. And the difference is that p is in L. Specifically, you can refer to L as r cross p, where r points, the position vector points to where the object is at any point in time. And if you cross product that with p, the momentum, mv, then you could find the angular momentum of some object orbiting around another. You could also say L is equal to I times omega, and you have to define a very specific direction for omega, which your book talks about there. M will ultimately just be replaced with I, the moment of inertia. And for instance, when you have Newton's second law, the summation of forces is equal to, assuming the forces and the mass is a constant. If that's the case, then you have the summation of the forces is equal to m times a. Well, in this case, the analog would be the summation of the torques. So we see that this Greek letter tau, which looks like a backwards cursive T, this Greek letter tau represents the torque. And if you add up all the torques acting on an object, then assuming those torques are constant and the moment of inertia is a constant, then you're going to get the summation of the torques is equal to I times alpha, where you can just solve for alpha as if it's another constant. However, if it's not, then you might have to do I times d omega dt. Or if you actually have a moment of inertia that change, you might have summation of the torques is equal to dl dt. So now that I've refreshed your memory on that, let's get started with this one. It says a car tire rotates through 8.4 revolutions in 3.00 seconds. So let's start off by solving this. I'll write down solution. And I usually use that as some time to either explain how we're going to solve it or give certain equations. So in this case, I'm going to start off by letting everybody know that the 8.4 revolutions is in fact a measure of theta, the angular displacement. So that's 8.4 revolutions. And I want to remind everybody that one revolution is equal to 360 degrees, or it equals 2 pi radians. So those are some numbers that we should know already and hopefully know, but just in case, I wanted to head and put them out here. So for part A, they're wanting to know through how many degrees did it rotate. So we're going to say A, theta equals 8.4 revolutions. This is like a unit conversion, so it's convenient for us to remember that the 8.4 is acting like a numerator, and I need to multiply it by a fraction that represents the value 1, and the value 1 has to be represented in such a way that the unit we have, the revolution, cancels out with a revolution. Therefore, the revolution must be in the bottom, so I'll put 1 revolution in the bottom, and you can see automatically how that's going to cancel out with that. And then, of course, since part A is asking for degrees, I'm just going to go ahead and put 360 on top. So it's 360 degrees per revolution. Now I have to multiply that by 8.4, and that'll give me the degrees, which is 3024. Now, 360 can be defined to be an infinite number of decimal places, but technically we only have two sig figs, so the 2,4 is actually only good to two sig figs. So really we should call that 3.0 times 10 to the third. And I find it's often better to just write out the word degrees because it's so easy to lose the actual symbol, a little floating circle. So anyways, that's part A. I think that's pretty straightforward. Feel free to ask me any questions if you have them. Part B, they want to know the same thing, but this time they want it in radians. So theta is equal to 8.4 revolutions. But again, we're wanting to find a fraction where the revolutions disappears. And what that tells me is I'm going to put the revolution in the bottom again. And then I'm going to put 2 pi radians on the top. Now, remember the radians is actually defined from this equation right here. S is equal to R times theta. So you see that theta is really S over R. So S could have, for instance, units of centimeters, then R would have units of centimeters, and you get centimeters per centimeters for the units of radians. So you see that the radian is not really a unit at all. It's really a pure number. So we often will throw out the radian or sometimes include the radian when we need it. And that's fair to do because it really is just a number. Okay. Now, it wouldn't make much sense to do that for a non-rotational thing, but if you did have a rotational thing, it would be worthwhile to do. So in this case, we're again seeing that the revolution cancels out with the revolution, and I'm going to get 8.4 times. Now I'm going to start with just the 2, and of course that would be 16.8. The reason why is sometimes people prefer their radian measures to be in pi units, so units of pi. So for instance, this could be 16.8 pi radians, and that one's perfectly acceptable. But just in case, I want to make sure everybody knows that what 16.8 pi radians really is a number. So I'm going to take that 16.8 and multiply it by 3.14159, and that gives me 52.77. Actually, I should call that 7/8 degrees. Or excuse me, 7/8 radians. Now, again, we only had two sig figs, so to be honest with you, this 7 and this 8 are not sig figs. They shouldn't really be included in there. But for the record, I'm going to go ahead and say all this is equal to theta, and I'm going to box it off. Now, in part C, I'd like to know what the average angular speed is, because this was actually rotated through 8.4 revolutions in 3.00 seconds. So I'm going to show you how I use regular kinematics to reason through this problem. What I know is V average is equal to delta x over delta t. So that would tell me that omega average would be equal to delta theta over delta t. And of course, we figured out that delta theta is specifically 8.4 revolutions per revolutions. So it's 8.4 revolutions. And we found that it was done in 3.00 seconds. So if I do that, I get 8.4 divided by 3 gives me 2.80 revolutions per second is the average angular speed. Of course, I could also have done 3024 degrees divided by 3 seconds. So that gives me 1008. And that would be degrees per second, which again is another measure of omega bar. So that's another way of expressing it. I could also do it in radians, so I'm going to take our 52.78 and I'm going to divide that by 3. So 52.78 radians divided by 3.00 seconds here. And that's going to give me 17.59. Again, 2 extra sig figs, and that's radians per second. So I just wanted to show you all the different ways we could actually express this angular speed using all the various units and whatnot. This red mark kind of jacked up, so let me fix this a little bit because you know me. So that was supposed to be a 52, so I'm going to put a 5 right there, and then I'm going to finish my little box by going like this. I know it's close enough. Okay. Any questions on that? Now, what it asked in part D was how many degrees are in one revolution, or excuse me, are in one radian. So we're going to do that now, and that's part D. So what we found was that 360 degrees is equal to 2 pi radians, which you can obviously simplify to 180 degrees is equal to pi radians. But you can actually simplify that further by dividing 180 by pi. And when you do that, you say 180 divided by 3.14159, and that gives me 57.30. And technically, this is true to any number of sig figs. So I'm going to say 56.30 degrees in 1 radian. Okay, so that's a figure you can keep and use on occasion. Of course, it actually has a mess load of more decimal places beyond that because pi obviously has an infinite number of decimal places. We've done basically everything using our symbols, so that looks like I kept it consistent with the use of the correct symbols for the angular quantities. Anybody have any questions on any of that? All right, well, let's jump to the next section. I do want to take a little bit of time. Let's do this real quick. I'm going to block this off as a separate problem, and then I'm going to write down some information that we need to know. So the one thing we needed to know was the equation that we learned in trig, which is S is equal to R times theta, which can sort of be thought of as the definition of radians. Okay, but if you took the derivative of that, then you'd get ds over dt is equal to r, assuming it's actually in a circular orbit so that r doesn't change with time. That would be equal to d theta over dt. Now that's all well and good, except now you can look at ds dt and realize that is really a arc length, which is the distance traveled along the edge of a circle. And taking the derivative of that distance traveled gives us the velocity. So that's going to be, and it's actually the tangential velocity. So that's going to be v is equal to r times omega. So that's another important equation. Similarly, we could take the derivative of both sides, and I'd get dv dt is equal to r d omega dt like that. When I do that, I get a, because again, we have a dv dt, is equal to r times alpha. So I should point out, by the way, that when I write these equations, these quantities mean something very specific. So this is the tangential velocity, and this is the tangential acceleration that you get when you're using these equations. So there's one of the equations. There's one of the equations. And I think you can tell that S equals R times theta has to be in, has to have theta in radians. So really, if you want to use V equals R times omega, you're really going to have to use radians per second for your angular speed, or radians per second for your angular acceleration. Now, we have all that, and it turns out that there's yet another type of acceleration, and that other type of acceleration is the one that actually keeps the object going in a circular path. And of course, we called that a centripetal, and that's equal to v squared over r. But this also has to be the tangent velocity. Okay, so that's another equation that you have to have at your ready. The other parallels I mentioned, by the way, are, let's see, I did say M goes to I. So you might think that the summation of the forces is equal to M times A becomes the summation of the torques, because I also said F becomes that backwards cursive T, the tau. Okay. So the summation of the torques is equal to, in this case, I times alpha. So that's another important equation we're using, and that equation is actually a dynamic equation because it actually gives us what causes the velocity, acceleration, and stuff of that sort. And it's usually good enough to just deal with a two-dimensional problem, in which case the vectors are sort of irrelevant, but in principle it could have vector symbols over it, so I could put like this and like this. And your book takes a little bit of time to define the direction of the omega vector and the direction of the alpha vector, for instance. There's also another version, though, that I should show you, and that is the summation of the forces is equal to dp dt. That becomes the summation of the torques is equal to dl dt, like that. So that's the analogous equation there. We also have something neat, specifically P, which equals mv, becomes L. Okay. So there's actually a couple chances for that. L can be equal to I omega, and we can put a vector symbol over both cases. But you can also have L is equal to R cross P. And that's more like if you wanted to calculate the orbital angular momentum of a planet, then you can imagine the sun, or the center of mass of the Earth, Moon, Sun system, basically the whole solar system. If you consider the center of mass of the entire solar system as the origin of coordinates, then the R vector would just be an R vector pointing from the center of mass to the center of the planet. And then you take a cross product of that with the momentum of the planet, and this is the momentum of the planet moving in orbit, not momentum of the planet spinning, and that would be L equals R cross P. So there's some more equations that come in handy. Now, obviously, if we want to know I and want to use I to calculate L, then we need to know what I is. So it turns out that if you have a bunch of discrete collections of masses, then it could be the summation from I equals 1 to n of m sub I r sub I squared, where r is really the distance perpendicular to the rotational axis from the rotational axis to the mass mi. So for instance, r sub I points from the rotation axis, whatever point is closest to that particular mass m sub I, and it's the distance between that rotation axis perpendicular to that rotation axis out to the m sub I, and you do that for each of them. But if you don't have a discrete collection, then it becomes the integral of r squared dm, and again our dm will be lambda dl, or sigma dA, the area r rho dV, the volume. So those are all useful as well. Anybody have any questions on that? Okay, hopefully from your experience with centers of mass, you understand enough about that lambda, sigma, and rho, and you'll understand it better as we go on as well. So let's go on to example 2, unless anybody has any questions. Anyone? Okay, so stand back for some more awesome handwriting. Sorry about that. Luckily, I'll read it to you. So it says a bald eagle can sight a rabbit, which is about 13 centimeters, from 3.2 kilometers. What is its angular resolution in radians? So what we want to know is what is the eagle's eye resolution, basically. Eagles have really good eyesight, as do all birds of prey, because they're birds of prey and they sort of need to eat stuff that they can see from long ways away. So we're going to go with that. I want to know what is its angular resolution in radians. What is it in fractions of a degree? So this is where I'm going to take the opportunity to show you that arc minutes is a 60th of a degree, and arc seconds is a 60th of an arc minute, which is a 3600th, of course, which is also a 3600th of an arc of a degree. So I'm going to use that. How big does an object on the moon have to be for an eagle to see it? This is a common misconception. Like you would think if we built, let's say Carolina's football field or something smaller would be like the Dean Smith Center at Chapel Hill. If I put those on the surface of the moon, you'd think that you could see them, but you can't. Okay, so we're going to see that. So let's work on our solution here. So solution. So the bald eagle can sight a rabbit. So what we're doing is we're picturing the bald eagle's eyeball, like so. Okay. And what we're imagining in this bald eagle is that, in fact, this is part of a circle of radius r, but in fact, the angle is going to be so small, it's going to be so small that the chord distance, which is that one right here, is approximately the same as the arc distance. So that's a key idea to think about. And I said the chord, and I want you to understand what chord means. Hopefully, y'all already know it, but chord length is the straight length from the two ends, and that's spelled CHORD. And then this part right here is S, and that's the arc length. They're both measured like in meters or anything like that. But the main thing is, if the angle's small enough, just like if the Earth is large enough, it feels pretty flat. The same thing happens here. If the angle's small enough, meaning we're like not very far from one part of the Earth to the other, that's why it looks flat. Well, similarly, if we're looking at a small enough angle, then that flat distance is about the same as that arc distance. So that's what we're going for here. Now, what we're saying is that the chord length, which would be the length for the actual rabbit, I'm going to say chord length is L. I'm going to say L is equal to 13.0 centimeters, which if we want to put everything in meters, that'd be 0.130 meters. Okay. And I'm going to say that is approximately equal to S. And of course, S is R times theta. And theta is what we want to know. That's the actual angular resolution. So what I can do is I can say theta, the angular resolution, is equal to S over R, which is approximately equal to L over R. And that is 0.130 meters divided by, in this case, the R is supposed to be 3.2 kilometers. So I'm going to say 3.2 times 10 to the third meters. That way they're both in meters. So I'll say 0.13 divided by 3.2 exponent 3. And that gives me 4.06 times 10 to the negative fifth radians. Because basically when you divide a matching unit by itself in this equation, it comes out in radians. Anybody have any questions on that? Now, this is not unlike a problem that your book did, and your book said the resolution was about 3 times 10 to the negative fourth radians for a particular bird's eye. My bird's eye is basically what I Googled to find for a bald eagle, so that's a pretty accurate measure, and in fact, it's probably pretty good. So we can see in part A what is the angular resolution in radians. So I'm going to say theta ang res is equal to 4.06 times 10 to the negative fifth radians. So that's our answer for part A. Now for part B, we want to know what that is in fractions of a degree. So what I'm going to do for part B is I'll put B right here and I'll say theta angular res is equal to 4.06 times 10 to the negative fifth radians. Again, this is a unit conversion, so it's sometimes a little more helpful to make sure it's created as a numerator of a fraction. So I just put it over 1. And now in this case, what I'm going to do is remind myself that pi radians, which I put on the bottom so they can cancel out, is actually equal to 180 degrees. And that's exactly 180 degrees. So however many sig figs I put in is how many I get out. That being said, we can see now that the radians cancels out with the radians. And I'm going to take this 4.06. By the way, it's 4.0625. I'll write that up here. That's actually, yeah, that's, 3 sig figs too good. So even that 6 is not really a sig fig. So anyways, I'm going to take this 4.0625 times 10 to the negative fifth, and I'm going to multiply it by 180. And then I'm going to divide it by 3.14159. So that's 6 sig figs. And that gives me 0.0023276 degrees. Okay, now as we said, it's really only 2 sig figs, so these guys are not sig figs at all. But this degree is not a convenient measure of degrees. In fact, it would be better to put it in arc minutes. So I could say times 1 degree is equal to 60 arc minutes. So if I multiply that by 60, I get 0.1397 arc minutes. That's still not necessarily very good, so I'm going to go ahead and say times 1 arc minute is equal to 60 arc seconds. So I can multiply this by 60 again, and this gives me 8.37. I should call this 8.380. So this is 8.380. Sorry about that. And that would be arc seconds. And this is all theta angular resolution for the eagle. So I can box off all this again so that you can see this eagle has an 8 arc minute, or excuse me, an 8 arc second angular resolution, which is really good. Anybody know what the angular resolution of the human eye is? I'm gonna double check. I want to say it's around
120.
point. Is it? I was thinking it was like around 12 or something like that arc minutes.
Never mind. I was thinking about angular or whatever.
You might be right. I don't know. So let's say angular resolution of a human eye, and see what the Google box tells me. It says 0.00, 1 arc minute. Sometimes you got to actually read the paragraphs to make sure. Basic properties. Some basic properties of the human eye are quick autofocus from distances of 25 centimeters for young people to 50 centimeters, most people 50 years and older, to infinity, an angular resolution of about 1 arc minute. So 1 arc minute versus this guy had 0.137 arc minutes. So they're a good fraction of 10 or higher angular resolution than us. So that's pretty impressive. And actually, 20 might have been, well, if you talk about arc minutes, then that's not that helpful. But anyways, so any questions about that one? We still got to do the moon thing. So what we want to do is we want to see how big something would have to be on the moon for the eagle to actually see it. So what I'm going to do is I'm going to imagine the Earth is right here, and I'm going to imagine the moon is way over here. And this, of course, is not to scale by any stretch of the imagination. In fact, what you need to know is whatever the radius of the Earth is. So if you imagine this right here is the radius of the Earth, then this distance from here to the center of the moon should be 60 Earth radii, and the symbol we normally use for the radius of the Earth is a circle with a plus in it. So this is R plus, like that. Now, what I will tell you is this is approximately 3.84 times 10 to the 5th kilometers. And that is, of course, 3.84 times 10 to the 8 meters, which you can see is a little bit bigger than a light second. So it takes light about 1.24 seconds to get from the surface of the moon to the surface of the Earth. By the way, the radius of the moon is way, way smaller than this distance, and the radius of the Earth is way, way smaller than this distance. So we can sort of pretend the eagle is sitting right at the center of the Earth, and the whatever we want to build there is right at the center of the moon. That's close enough, in other words. So when I do that, what happens is I get a very specific cone of sight, if you will, which this thing just obviously made parallel for no darn reason whatsoever, but that's okay. I think I can fix it by doing it like that. And we want it to be able to see it. And what we say is this angle right here. Whoa, didn't mean to do that. What we want to say is this angle right here, theta, is equal to 4.06 times 10 to the negative 5th radians. And the r, of course, is equal to r being the distance here, not that other r. This is 3.84 times 10 to the 8th meters. So basically, I can figure out the arc length here, which is so close to the chord length that we can find it. So S is equal to R times theta. And in this case, it's 3.84 times 10 to the 8th meters. times 4.06 times 10 to the negative fifth radians. And this is going to give us 3.84 e to the eighth. Whoa, Nelly. 3.84 e to the eighth times 4.0625 e to the negative fifth. And that gives me 15,600 meters. So in other words, it would have to be about 16 kilometers across for even an eagle to see it. Any questions on that? All right, so that's kind of a big deal. The moon is so far away that an eagle, which can see about 10 times better than we can only see something if it's at least about 16 kilometers across. That's obviously bigger than any football stadium we've ever built, including the British version of the word football. So even the fancy stuff that we've got in Dubai and stuff like that is quite small compared to this. Now it's more on the order of, the Great Wall of China could clearly be seen, but that has to be a really long way away. I think the Great Wall of China is on the order of hundreds of miles. So, anyways, anybody have any questions on that? Okay. Actually, I just realized my chat window's not up for in case anybody talked to me. You can go ahead and chat me your first and last name for your role if you'd like as well. Looks like no one has any questions, so I'm going to go ahead and move on to the next example, which I started and did not finish. So in this case, what we're talking about is a merry-go-round has a 3-meter radius, and starting from rest experiences a constant acceleration of 0.080 radians per second every second. If it accelerates for 9.00 seconds, what will its angular velocity be? B, through what angle will it have rotated? Okay, so that's the problem we're going to work. Solution. So in this case, we're going to work off first to find out what its angular velocity will be. And what we know is angular speed is our angular velocity. That's what we're wanting to know. And we're also wanting to know through what angle is that going to actually turn, and that's part B, and we're going to call that theta. Okay. Now, in doing part A, what I'm going to do is I realize that if I want to know the angular speed, one equation I've used in the past in linear motion was V is equal to V0 plus AT. So from this, my analog tells me that omega must be equal to omega 0 plus alpha t, and that's exactly correct. So we can use that. Okay, it's not necessarily the only way, but it's the way that I've chosen to use it. So what we know is the initial velocity, since it's starting from rest, the initial velocity is 0 radians per second, plus now we have the alpha, and the alpha is 0.080 radians per second every second, which is also the same thing as radians per second squared, but I told you before why we choose to do that, to say it that way. So this is going to be times 9.00 seconds. So when I multiply 9 times 0.08, that's going to become 0.72. So what we'll say is omega equals 0.72. And that looks like all the sig figs we have, so I'll put an extra 0 on the end, and that's radians per second, which also equals, remember, a radian is in fact 1 pi radian is in fact 300 or 180 degrees. So if I chose to divide that by pi, 0.08 times 9 is 0.72. If I divide that by pi, 3.14159, that gives me 0.229. And now I've got to multiply it by 180. So times 180, that gives me 41.26. And that is actually degrees per second. And we could actually put it in, for instance, a more common term would be like revolutions per minute. So in this case, rather than putting that equals there, I'm going to go ahead and show you the work. Obviously, this one was 180 degrees divided by pi radians. That was the conversion factor that got me to there. This one, I'm going to take and say that 360 degrees is equal to 1 revolution. And I'm also going to say that 60 seconds is equal to 1 minute, so we can get it out in revolutions per minute. So if I take the 41.26 and divide it by 360, and then multiply that by 60, I get 6.875. And that's revolutions per minute, which we'd also write as RPMs, like on your tachometer of your car. Any questions on that? Okay. So I just wanted to give you a couple different measurements so you can sort of relate it to everyday life stuff that you might encounter, that kind of thing. So hopefully doing those different conversions helped you a little bit. B, through what angle will it have to rotate? Well, I know if someone asks me a question like that in linear motion, I immediately think the equation x is equal to 1/2 at squared plus v0t plus x0. And of course, the rotational analog of that is theta is equal to 1/2 alpha t squared plus omega 0t plus theta 0. So I could definitely use that. And in so doing, I'm going to say theta equals 1/2. The alpha is 0.080 radians per second every second times t squared, which would be 9.00 seconds squared, plus 0 because the angular velocity was initially 0, plus 0, which basically we can always call the theta 0 or the x 0 0, so that's not a problem. And when I do this, I get 0.5 times 0.08 times 81, which is 9 squared, gives me 3.24. So this is going to be 3.24. And I really only had 2 sig figs there, so I should underline that 4. That should come out in 3.24 radians is what I actually rotated through. Now I can use the fact that 1 radian is 57.30 degrees. So I could do that if I wanted. So I could say 1 radian is equal to 57.30 degrees. That's easy enough. 3.24 times 57.30 gives me 185.7 degrees. Okay, 2 extra sig figs there as well. And we could also put it in revolutions if we wanted to, by realizing that 360 degrees is equal to 1 revolution. So dividing that by 360, which obviously is nowhere near 360, we're going to get about a half. So that's 0.5157. Oops. 0.5157 revolutions. Okay. So that's probably way more than you really wanted to know, but we've done it. And of course, I could also just call this theta, which is, the variable that's in that we're using here. Anybody have any questions on that one? Now, a good check is to see if one of your other equations might have actually been good. So what I do know is that v squared is equal to v0 squared plus 2a x minus x0. That's one of our kinematic equations. Therefore, I should be able to use a rotational analog, which apparently would be omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. And again, we're always allowed to assume the initial theta or the initial x is 0. In this case, it did start from rest, so that's 0. So ultimately, in this case, what I get is theta would be equal to omega squared over 2 alpha. So omega being the final angular speed, we could say is, since we have the alpha in radians, I'm going to go ahead and use 0.720 radians per second. That's going to have to be squared divided by 2 times 0.080 radians per second, like so. And in this case, I'll say 0.72 squared divided by 2 times 0.080, and that gives me 3.24 radians, which is exactly the answer we got before. So that gives us a little confidence that we did it correctly. So yes, all those equations that we used in chapter 2 and 3, we can use again now. And all we have to do is just make the translation between the analogous variables. Anybody have any questions on that? Okay. Well, there's another problem, and I've sort of made this up a little bit. Let's see what I can do. This was example 3. We got plenty of time. So example 4. So consider a disk of radius 4.00 meters that rotates with an angular speed or angular velocity of omega equals, let's say, 2.4 plus 3.6 t squared, all that in radians per second. At t equals 0, actually, let's do t equals a whole number. Let's say at t equals 3.00 seconds. What is A, the angular acceleration, and B, the angular velocity. Let's say part C, if theta of t equals 0 is 3.75 radians, what is theta of t? Okay, so I'm trying to wrap it up and remind you guys that your next face-to-face, like all tests in physics, is comprehensive. So I could give you, for instance, the acceleration as a function of time and ask you to find the velocity as a function of time, giving you certain initial conditions, and ask you to find the position as a function of time, and giving you certain initial conditions. This is sort of like that right now. So let's see what we can do. Here's our solution. Anybody have any questions about the problem before we get started? Okay, so what we know is, for starters, we know that alpha is equal to d omega over dt, and alpha is our angular acceleration, which is what we want to know in part A. So I'll do that. So d omega over dt, notice the derivative of 2.4 radians per second with respect to time is 0. But the derivative of 3.6 t squared would be 7.2 t. And of course, that comes out again in, well, in this case, it'll just be in radians per second, like that. Which, like I said before, you can write it as, oops, I wrote 7.2 correctly, but the other one I wrote something else. What I was saying is you can write as 7.2 radians per second, but in this case, I'm actually trying to write it in a more convenient way. So that looks pretty good. Now I can go ahead and figure out what what alpha is at t equal 3.00 seconds. So if I quit erasing things, so alpha of 3.00 seconds is equal to 7.2 radians per second squared times 3.00 seconds, which 3 times 7 is 21, and 3 times 0.2 is 6. So this will be 21.6 radians per second. And that's radians per second squared. Yeah, so radians per second squared means this in here has to be radians per second cubed, just to make that work out. But the whole thing works out now. So we get radians per second like this. Any questions on that one? Sorry about the little bit of a flub. All right, so I can circle this off, and I can say this is, in fact, alpha of 3.00 seconds, and that's one extra sig fig right there. B, what we want to know is the angular velocity at 3 seconds. So the angular velocity, omega, is equal to 2.4 plus 3.6 t squared times radians per second. And if I plug this value in, I get 2.4 plus 3.6. T squared would be 3.00 seconds squared. Obviously, when I pull that second squared in there, that's just going to make the final result radians per second, which is what we expect for that. So that tells us these units must be radians per second, and this unit must be radians per second squared or cubed. Let's see. Yeah, radians per second cubed. So that when we multiply it by time squared, I just get a radian per second. So yeah, that works. So I'm going to take 3.6 times 3 times 3, and then I'm going to add to that 2.4. That's going to give me 34.8. Radians per second is the final angular speed at the end of 3 seconds. So that's omega of 3.00 seconds. Anybody have any questions on that one? Okay. Well, with this, we can actually ask a few more things. Let me add part D. Ooh, wait a second. I still need to do part C. Let's do part C first. I forgot that I'd done that. So if theta of t equals 0 is 3.75 radians per second, what is theta of t? So what we know is omega is equal to d theta over dt, and we know that specifically because we already knew that v is equal to dx dt, so we just use the analog again. The analog of v is omega, the analog of x is theta, so I can just integrate this stuff. So I'm going to say 2.4, let's ignore the units for right now, but 2.4 plus 3.6 t squared is equal to d theta over dt. If I multiply both sides by dt, I get the, and integrate, I get the integral of 2.4 plus 3.6 t squared dt is equal to the integral d theta over dt, and that's from t equals 0 to just plain t. And actually, that corresponds, of course, to theta of t, and this corresponds to theta of 0. Okay, this one's going to be from t equals 0 to any time t later. When I integrate that, it's going to become 2.4t plus, that's going to integrate to 1/3 t cubed, and of course 1/3 of 3.6 is 1.2, so this is going to become 1.2 t cubed. And that's going to be evaluated from t equals 0 to t. And this is just going to be theta of t minus theta of 0, which we were already given. Theta of 0 is equal to 3.75 radians. So now we can say theta of t is going to be equal to 1.2 t cubed plus 2.4t plus 3.75 radians. I should specify that this unit is going to have to be radians per second, and then this unit is going to have to be radians per second cubed, like that. But that is the theta as a function of time that we got there. Okay. Now for part D, which I didn't write, but now I am, what is a total? Okay. So that's something we can do. And I mentioned this in class before, so let me remind you guys that we could have, for instance, a arc that something is traveling along. So that's one part of the arc of a circle, say. And let's say at this point right here, I'm going to say that's the x-axis and the origin and the y-axis. And because of that, we're going to have a tangential acceleration this way and a centripetal acceleration this way. And we know that A tangential is equal to R times alpha. And we know that A centripetal is equal to V squared over R. Okay. And we already know the actual radius of the disk. So we're actually talking about specifically the total acceleration of a point on the outer disk of, or the outer edge of the disk. So I can say that A total is equal to, notice the way I drew the coordinate system at that particular point, we can see that the tangential will point in the positive I hat direction and the centripetal will point in the negative J hat direction. So A is equal to R times R times alpha. We already found that alpha was equal to 21.6. So I'm going to say 21.6 times 4.00 meters gives me 86.4. And that's meters per second every second in the I hat component, I hat direction. And I'm just going to write this in case anybody looks back and doesn't realize that I did 4.00 meters times 21.6 radians per second. Okay. And then minus, in this case, I've got to do V squared over R. Well, V is the tangential speed. And of course, V is equal to R times theta, or excuse me, R times omega. Stupid me. So I already know what omega is. Omega is 34.8. So I'm going to take 34.8 and I'm going to square it. Oops, not first. I'm going to multiply it by 4.00 meters. That's going to give me 139.2 meters per second. Now I got to square that and divide it by the radius. So now I'm going to square it and then divide it by 4.00. And that gives me 4,844.16. So 4,844 meters per second every second is what's required to keep it in the circle. And of course, that'll point in the negative Y direction. And I'm just going to remind everybody that I did V squared over R for that quantity. Anybody have any questions on that one? All right, we're up to 626. I guess what could be right, I want to tell you, your book talks about vector nature of angular quantities. And really, if you're talking about something rotating, there's no good direction to assume that something rotating like this would be in, because they're all completely arbitrary. So if I chose that way, well, that's arbitrary. If I chose that way, that's arbitrary. If I chose that way, that's all these different directions are arbitrary. But if you choose perpendicular to the plane of rotation, you only have two choices, and that is up or down. And we as humans actually have two hands. So we can choose one of them somewhat arbitrarily and let that define us. So if we have an object that's going around this way, which looking from above is counterclockwise, looking from below is clockwise, then all I do is I take my right hand and I curl my fingers in the direction it's rotating. Remember, looking from above, that would be counterclockwise. Then my thumb points in that direction. So if something's rotating this way, counterclockwise as seen from above, then the omega vector should point directly upward. That's it. That's the way we define the direction for a rotational velocity. Okay, the alphas can be sort of similar as well. and your book talks about that. I will warn you that it is a pseudo vector, so you can look at, for instance, if you have a velocity this way and you put that in front of a mirror, it still points that way. Whereas if you have a angular velocity that's going this way, then the angular velocity direction should point to the right. Now, if you look at a mirror image of that, that thing is rotating that way. Therefore, you'd expect it to point this direction. But in fact, the mirror said it pushes outside of the mirror said it pushed this way. So that's why it's a pseudo vector. So anything that has that kind of property where it has to flip directions when you look at a mirror image of it, then that's called a pseudo or axial vector. Okay. It's more of a something you should just know about as opposed to something that you really have to worry about day in and day out. But it does give you the actual directions. Your book does give you some more kinematic problems that you can solve. I want to jump on into rotational dynamics and torque. So what I'm going to tell you is that just like L, remember I told you that L is equal to, this is the angular momentum, is equal to R cross P. Well, it turns out that we can define the torque as R cross F. Okay. And that's really nice because it means that in magnitude, the magnitude of the torque, which you can always take and put absolute value bars around a vector, and that'll mean the magnitude of it. But you can also, to save yourself some writing, you can just write the symbol for the vector without the arrow over top of it, and that would also mean it. But that is going to be R times F times the sine of the angle between them when they're tail to tail. So for instance, you could say that this is R vector and this is F vector, and that this is the angle between them, tail to tail. But in fact, its direction, on the other hand, would be into the page. So I would say by a right-hand rule, I would say by a right-hand rule, this would be the torque vector, and that is in fact perpendicular to this guy, and it's also perpendicular to this guy, and it's going into the board or into page. Because it has to be right-handed where you can take, one way of doing it is you can take and make your hand like this. Notice they're all three mutually perpendicular directions. So the first vector is R, that goes the direction of your index finger. The second direction is F, that goes the direction of your middle finger. And then the answer, the actual cross product, is the direction of your thumb. So when I have R and F like this, then we see it points into the board like that. Okay. But another thing that it happens to equal, and this comes in really handy and can save you a lot of calculational effort and a lot of geometry. It's also equal to the component of R perpendicular to the F, or it's equal to the component of F perpendicular to the R, because that's what sine does. Sine picks off the perpendicular component. So all these are nice new expressions we can make use of as follows. Okay. So now that we have that, we can also express what torque is just in terms of everyday life. If you're trying, for instance, to pedal a bicycle, then you might know that that would be like your chain wheel, what we call a chain wheel, or your sprocket. And you'd have the chain running back like this and the chain running back like that. And then you'd have, in fact, the crank, which is something like that. Okay. And your pedal would be something like that. If you've ridden a bike before, then you know you've sort of worked it out in your on your own that if I actually push my force straight downward and the pedal arm like this is perpendicular to each other, that gives me my maximum torque. And the reason is, as you can see, torque is equal to R cross F. What is R? Well, R is a vector that points from the center of rotation to the point of application of the force. So that's our R vector. It's called a lever arm. And of course, you can see it does point from center of rotation to point of application of the force. So you can tell, hopefully, that if I were to replace this sprocket setup with a crankshaft that was only this long, you'd see that the torque is much less there. So you can see that torque should be proportional to R, the distance from the center of rotation to the point of application of the force. You can also see that it's directly related to uh, being a maxima when the force is at a 90-degree angle to the R. You can also see that it depends not only on the R, but also on the force. So, for instance, if I got on top of this pedal and pushed down, I weigh nearly 300 pounds. A lot of you weigh nearly 100 pounds, so I could have 3 times as much force and therefore times as much torque. So, you see that torque should be proportional to R and it should be proportional to F, and then it should be proportional to the sine theta, because theta equals 90 degrees implies sine theta equals a max value. Okay, so that's the key to understanding torque. If you want to then apply torque, then it's just a matter of figuring out which versions of these equations you want. For instance, if they give you an R vector and an F vector, then that's a pretty telltale sign that they want you to just go ahead and do a cross product. But if the R vector and the F vector only have, one component, that's a monumental waste of time. So just to refresh, the torque is equal to R cross F means it's equal to a determinant of a matrix, and that matrix is supposed to have a I hat for the first vector, the top left, the first row, first column, a J hat for the first row, second column, and a K hat for the first row, third column. Then it has RX for the second row, second column, or excuse me, second row, first column, RY, second row, second column, RZ, second row, third column, and then FX, FY, FZ as the third row. So that's the actual method you go by calculating a cross product using a determinant. And I've explained this before, but just to reiterate, this turns out if you want to expand it upon I, J, and K, you can say it's I vector times R, Y, F, Z minus R, Z, F, Y plus J vector. Now, this one's the one that would have the negative sign normally, so I have to do it in that opposite order. So it's going to be RZFX minus RXFZ, and then plus K hat. This one has a normal sign, so I'll do RXFY minus RYFX, and that's the formula for that one as well. So I can go ahead and just add this in here. Any questions on that? All right, we only have like 3 minutes left, so I'm not going to try to fit in more examples, but you are in a good spot now. You can actually do that. I only have 3 minutes. Well, let me do you something real quick. What I'm going to do real quick is this. I'm going to say I is equal to the integral R squared dm. And what I'm going to do is imagine that along the x-axis, I have a rod that is uniformly, oops, has its mass uniformly distributed. So this is a rod whose mass is uniformly distributed. So what I'm going to do is call this little bit right here, that's going to be my differential mass element. And I'm going to say it's lambda times dx. And since this, I'm going to say has a length L and a mass m, I'm going to say that lambda is m over L times dx. And then this distance from here to here is actually x. So what I get is the integral of x squared lambda dx from x equals 0 to L will be lambda times the integral of x squared dx from 0 to L. And that gives me, of course, 1/3 lambda L cubed. So if I plug all this back in, 1/3, and then lambda is m over L times L cubed, you see that the moment of inertia, I, is equal to 1/3 ml squared. So that's the way you can actually do the integral to figure out what the moment of inertia is. And I've used up my time appropriately. You guys are free to go 1 whole minute early. Make sure you typed your name in the chat before you go, but you are free to go. And good luck on your exams, everybody.
Thank you. Have a good evening.
What units are the exam gonna be on? Or what
It'll
chapter?
go through all of chapter 9.
Oh, only chapter 9? Okay.
Yeah, I didn't do 10 yet for that. So just 1 through 9.
Okay. Thank you.
All right. Anybody else have any questions? I'm going to check that real quick just to make sure I made the testament accordingly.
I missed the first couple minutes of this lecture. I was wondering if we had to do anything because I missed lab this morning, if there's any sort of like makeup.
Oh, gotcha. So no, I actually held class, and for the 241, I had several people show up for it. It's actually been posted online, so you can check out what we did. But we didn't do nearly as much stuff as I did here, so coming today more than made up for it.
Okay, so I don't need to go in Canvas and like do the actual lab portion of it from
Right? Yeah.
this morning.
Yeah, we didn't do a lab, so you're golden on that.
Okay, so then we'll just pick up with the next lab.
Yep.
After the test next Monday.
Exactly.
Okay. Awesome. All right. Thank you so much.
All right. You're welcome. Talk to you later. Bye-bye.
Talk to you later. Bye.
That looks like it. So I'm going to go ahead and stop. I will let everybody know, those of you who are listening, our PHY 241 class that meets face to face on Mondays and Wednesdays, their test isn't until next week. So I think I had actually chosen to put 9 and 10 on that one. But the class that's meeting tonight, the internet class, should only go through 9. I'm checking my practice tests right now to make sure that's set up the way it is. And it looks like I've got something odd there. So I'll deal with that. Y'all have a good one. Talk to you later. Bye, everybody.